Alright, welcome back. This video is about variance and variance positions in Scala. These topics are very important for Zio, which is why this topic deserves its own lesson. If you're well versed with variance already, feel free to skip this video or watch it in high speed, although I do recommend you stick around even as a refresher. So without further ado, let me get back to our soon to become our favorite project. And under the recap package, I'm going to create a Scala application and I'm going to call this variance. I'm going to make it an object, and I'm going to type in a main method just in case we need to test some stuff, but this is mostly compile time stuff. Now, the Zio family of libraries embraces object-oriented programming and subtyping, and variance is a Scala feature that will allow subtyping for generics as well. This is a very powerful feature, and we're going to show it here. Now, we demonstrate variance in the Scala Advanced course, so if you went through the Advanced Scala course already, you can skip this lesson because we're going to recap the same concepts. So in object-oriented programming, we rely on substitution. And substitution relies on subtyping. So if I define a class called animal and a class called dog with a name as a string, which extends animal, then we say that if we define a variable of type animal, we can replace that, we can substitute that with a dog. So if I define, let's call this an animal, which is an animal, and I'm going to create a new dog with the name Lassie, for instance, this is a proper substitution. I'm actually going to save the new dog Lassie in its own variable, so I'm going to call this Lassie. And this is a new dog, and this val animal typed with animal can be replaced with a dog, which is Lassie. And this is regular object-oriented substitution that you can also find in languages like Java. Now, variance is the extension of this substitution model to generic types as well. And I'm going to ask what I like to call the variance question for the list type. And the variance question sounds something like this. If we have the class dog to be a subtype of animal, then the question is, should a list of dog be a subtype of list of animal? So should a list of dog be a subtype of list of animal? And in real life, conceptually, intuitively, the answer should be yes. But there are many answers, many possible answers to this variance question. Let's start with the answer yes. And the data types for which the answer to the variance question is yes are called covariant. That is to say, if I define a val Lassie with a new dog Lassie, let me define a bunch of other dogs. Let's call this Hachi as new dog with the name Hachi. And I'm going to define another one, let's say Laika, as new dog with the name Laika. Then if I define a list of animals, let's call this some animals, which is of type list animal, I can define that as a list with these three dogs, Lassie, Hachi, and Laika. And this expression is of type list of dog, which is a proper substitution for a list of animal. Intuitively, this makes sense. So if you are requesting a list of animals and you're being given a list of dogs, that makes sense because the dogs are animals. Now, the data types for which this substitution is possible are called covariant, and we define these types. I'm going to define a trait or a class. I'm going to call this my list, and I'm going to add a plus sign to the generic type argument. The plus sign denotes the fact that this type is covariant. So in other words, I can say my animal list as a my list of animal equals, and on the right-hand side, I can define an expression which returns in my list of a subtype. So I'm going to say my list of dog. And if this is true in technical terms, we say that my list, the type, is covariant in the type argument for which we have the plus modifier here. So we have answered yes to the variance question, and the answer yes denotes the plus modifier to the generic type argument. Another possible answer to the variance question is no, which means that the type in question is invariant. For instance, I'm going to define a trait called semigroup. And the trait semigroup takes a type argument A, and this denotes a combination function. So I'm going to have a combine method, combine, where we have two arguments of type A and we return another value of type A. This is the mathematical definition of a semigroup. Now, the semigroup doesn't make sense to add plus modifiers here because two semigroups of different types have no subtype relationships between them. Another example of invariance is all generics in Java. So, for instance, if I have a Java list as a Java util array list, for instance, as array list of animal, as a new Java util array list of type dog, for instance. This is not possible because the array list type in Java is invariant. In fact, Java has no concept of variance in the style that Scala does. Java has wildcards, which has a very limited substitution model. That is to say that an invariant generic type will involve no subtype relationship between two generic types typed with different type arguments, in this case animal and dog. Notice that we have a type mismatch here. So at this point, we've answered yes and no to the variance question. And for yes, we have covariant types, and for no, we have invariant types. There is a third answer to the variance question. I like to call this hell no. And that is a concept that is called contravariance. And contravariance is the opposite of covariance, meaning that if dog is a subtype of animal, then the thing of dog is a supertype of the thing of animal. And as an example, I'm going to give a vet. So I'm going to define a trait called vet, which has a negative sign before the generic type argument. And let's say that the vet has a method to heal an animal of type A, and this returns, let's say, a Boolean if the vet was successful. Now, in this case, if I define my vet as a vet of type dog, then I can replace this vet of dog with a vet of animals. Notice that we are going to use the inverse subtyping. So I'm going to have a new vet of animal where the heal method will return something along the lines of, let's say, print line, here you go. You're good now. And then let's say I'm going to return true. Notice that this subtype is possible. We define this as a vet of dog and we replace that with a vet of animal. So notice that the animal is the supertype, but the vet of animal is the subtype of vet of dog. This is a little bit counterintuitive. And in order to dispel this counterintuitiveness, if we are requesting a vet of dog, we are obtaining a vet of animal which can treat any animal, including a dog. So a vet of animal is in some respects better than a vet of dog because this vet of animal can treat any animal, therefore it can treat dogs too. In technical terms, because dog is a subtype of animal, then we have vet of dog being a supertype of vet of animal. So in this very specific sense, vet of animal is quote-unquote better than a vet of dog in the sense that this vet can treat any animal, therefore my dog as well. And obviously, because this vet is typed with vet of dog, I can pass a dog to its heal method. So I can say healing, let's say Lassie, as my vet dot heal with Lassie as the argument. And this is possible because Lassie is a dog, my vet is a vet of dog, therefore heal can take the dog as an argument and this returns true. Alright, so we have the three possible answers to the variance question. We have yes with covariant types, no with invariant types, and hell no with contravariant types. And we denote contravariant types with a negative sign before the generic type argument. Now the next question is, and it's quite intuitive, is when we are defining generic types, how do we pick covariance, contravariance, or invariance for our generic types? Here's a rule of thumb. First of all, if the type produces or otherwise retrieves values of type A, such as lists, for instance, then the type should be Covariant. So producers should be covariant. If the type consumes or otherwise acts on values of type A, so consumers such as serializers, processors, or in this case a vet which acts upon an animal to make it well again, so a vet, then the type should be contravariant. So producers should be covariant, consumers should be contravariant, and otherwise invariant. So if there's something that I want you to take away from this lesson, it's this rule of thumb over here. Okay, now, in the presence of variance, which is a very powerful Scala feature as you can probably guess, this poses some problems with respect to type checking in the compiler, and those are called variance positions. That is because not all syntactic structures are well formed in the presence of variance, because otherwise the compiler will not be able to do proper type checking. And I'm going to demonstrate some situations where variance can pose a problem. And I'm going to define a class. I'm going to call this vet2 so that we don't conflict with the other vet. We are going to make this contravariant as we shown before. And I'm going to add a val field in this vet. Let's call this favorite animal, which is of type A. Now notice that we get a compiler error, and if we remove the negative modifier from the generic type argument, the compiler is happy. So it has something to do with the contravariance here. And the compiler error says contravariant type A occurs in covariant position in type A of value favorite animal, which is psychobabble. This is a very cryptic kind of error, and I'm going to explain what this error means. Now, assume for a moment that this thing compiled. So assume that this was a well-formed expression. Then I would be able to write the following code. First of all, let me define a cat class. So I'm going to define a class called cat, which extends animal. Let's assume that we have something like that. I'm going to define an instance of cat. I'm going to call this Garfield, and this is going to be a new cat. So in this case, I'm going to define a vet. I'm going to call this the vet, which is of type vet animal. And I'm going to instantiate that as a new vet of type animal. And by vet, I mean this little thing which doesn't compile. So a vet2 of type animal. And I'm going to pass my little favorite animal, which is a cat, which I'm going to use Garfield here. So I'm going to have Garfield as the appropriate field because Garfield is an animal being a cat. Cool. So because vet2 is contravariant, then I can do the substitution that I did before. So I'm going to define my dog vet, which is a vet of type dog. And on the right-hand side, because we have contravariance, I can pass a vet of animal. So I'm going to use the vet here. Now, in theory, because this dog vet is a vet2 of type dog, I should be able to retrieve its favorite animal. So I'm going to have my favorite animal, which should be of type dog because this dog vet is of type vet2 dog. Therefore, the favorite animal should be of type dog. And I'm going to say dog vet dot favorite animal. But because dog vet is the vet whose favorite animal is a cat, I have a type mismatch here because I should be able to guarantee that the favorite animal should be a dog, but the favorite animal is a cat. So this must be a dog, so we have a type conflict. So the compiler is unable to force the equality between the generic type argument and the type of the favorite animal, and also give the freedom to do the substitution here guaranteed by the contravariance annotation. So we say that the types of val fields are in covariant position. That is to say, only covariant types can have val fields using their generic types. Var fields are also in covariant position for the same reason. Now, var fields are also in the opposite position. Let me give an example. So I'm going to define, let's call this a class. I'm going to call this mutable container, which has a plus annotation to the generic type argument. And I'm going to have a var with contents as a value of type A. Notice that we have an equivalent compiler error saying covariant type A occurs in contravariant position in type A of value contents, meaning that the type variable here, the type A associated with a variable, is also in a contravariant position. I'm going to demonstrate why by giving a counterexample where if the code compiled, then we would get into some sort of type conflict. So let me define a container of animal, which is a mutable container of type animal. And because this is covariant, I'm going to use a mutable container of a subtype, which is, let's say, a dog. And because this is a new mutable container of type dog, I have to construct it with a dog. So I'm going to have a new dog inside. But this container animal, because it's a mutable container typed with a general type animal, I can then say container animal dot contents, which is a variable, can be reassigned to another animal, which is a new cat. This is, again, a type conflict. Because due to the fact that this is a mutable container of animal, this compiler should be able to give me the freedom to associate the contents variable to any kind of animal that I like, but due to covariance, I also have to guarantee that the type for which the mutable container was constructed must have the same type, which the compiler is unable to enforce, which is why we have a type conflict, and we say that the types of var fields are also in a contravariant position. Now, this poses an interesting question because variable fields are in covariant position because they're in the same situation as values in the previous example, but they're also in a contravariant position because of what we've just shown here. So how are variables compatible with variance at all? And the answer is variables are incompatible with covariance or contravariance. Variable fields are only applicable for invariant types. The next case is the types of methods, and in this particular example, I'm going to show you types of method arguments. And I'm going to show you that the types of method arguments are in contravariant position. Contravariant position means that types of method arguments are incompatible with covariant types. So let's assume that I define my class. I'm going to call this my little list, which is a plus a, and I'm going to call this my list 2 because we are in a conflicting naming with the previous mylist. And I'm going to define a simple add method. Add with element of type A, and this should return a mylist of type A. Being a list, we should be able to add an element to this list and return a new list as a result. However, the compiler is very unhappy with that, saying that covariant type A occurs in contravariant position in type A of value element. What the hell, compiler? Come on. I should be able to add an element of type A and return a mylist A. However, the addition or any kind of method that consumes a type A, given the fact that the original type is covariant, is impossible. And I'm going to show you why that is the case. Now, probably your intuition may already start to trigger because consuming an element is a behavior specific to contravariant types. And that is the case because of what I'm going to show you. So let's say that I'm defining my animals list. So animals as a mylist2 of type animal. And I'm going to say new mylist2 of type cat. This is possible because mylist2 is covariant. I can offer this kind of substitution. Now, let's say that I'm going to say bigger list of animals. Again, as a mylist2 of type animal. As animals dot add, and because animals is typed as mylist2 of animal, therefore I can add an element of type A, which is animal. So I can say new dog, which is a mylist2 of animal. However, the compiler has to enforce the fact that because animals was constructed as a mylist2 of cat, I should never be able to add anything but cats in this list. So we again have a type conflict. In other words, the addition of an element, because it's a contravariant behavior, should only be applicable to contravariant types, which is the case here for vet. So notice that the healing, which consumes an animal, is applicable to the vet because it's a contravariant type. Now, if we do want to add an element to a list which is covariant, we need to give the compiler some freedom. So the solution to that would be to make mylist2 add an element, but of a different type, which is inferred by the compiler. So I'm going to add a type argument here that I'm going to call b. So this is going to be an element of type b, and the end result is going to be a mylist of b, under the restriction that b must be a supertype of a. And I'm going to leave this implementation blank so that the compiler doesn't yell at me for a different reason. But notice that in this case, the compiler is happy with my signature because the solution is to widen the type argument. And intuitively, I should be able to do that because if I have a list of cats and if I add a dog inside, what I will get in the end is a list of a different type, of type B, which is a supertype of both cats and dogs, which is in this case animals. So if I add a dog to a list of cats, I will obtain a list of animals because animal is the first type which correctly describes all the elements in this list. So, as you can notice, some interesting problems with variance and variance positions. One final case, which is method return types. And they are in covariant position, meaning that they're incompatible with contravariant types. And as before, let me show you with an example. So let me define a class. I'm going to call this vet2. I'm going to make this contravariant because of what we have shown earlier. And I'm going to add a method. Let's call this rescue animal. And this returns an element of type A. And I'm going to make this abstract because I don't want the compiler to yell at me for the wrong reason. And the compiler error says contravariant type A occurs in covariant position in type A of value rescue animal. So notice that the return types, which is a production method being a covariant behavior, is incompatible with vet2 being a contravariant type. And I'm going to show you another example why that is the case. So let's assume that this thing compiled. Then in this case, I'm going to define my val, let's call this vet, as a vet2 of type animal, as a new vet2 of type animal. So notice that in this case, the type arguments are the same, where, and I'm going to override this little method, so I'm going to say rescue animal should return an animal, but I'm going to return a new cat. So the rescue animal method should return an animal, and I'm producing an animal. This expression is of the proper type. Now, due to the fact that vet2 is contravariant, then I can say lassie vet as a vet2 of type dog equals new vet2 of type animal, and I'm going to use my little vet here as I've demonstrated earlier. So because of the contravariant relationship, I can replace the vet2 of dog with a vet of animal. Now, if I want to obtain a rescue dog as a dog, because I can call lassie vet's rescue animal method, then rescue animal should be returning a dog. However, due to the implementation of the vet that I've replaced it with, this will return a cat. So this must return a dog, but it returns a cat. Again, a type conflict. And the way to solve this problem is in some way opposite to the solution for the problem before, and that is to narrow the return type in this abstract class. So if I define that with rescue animal returning the type A, I'm going to add this type argument B here, and this will return an element of type B, and this B must be a subtype of A. Now, the actual implementation of such a rescue animal method might be a whole different story, but at least it makes the compiler happy. So there you have it, folks, variance and variance positions in Scala. We're going to use them a lot in this course. Waiting for you in the next video.